Good morning, everybody. Hope you're doing well and had a good weekend. Uh, Here we are ready to start a brand new week and talk about exponential and logarithmic equations. We've been looking at the definition of exponential functions and logarithms and their properties, so now we apply it to be able to solve problems. So one of the methods that we can use is by using the idea of a common base. And we actually did this a little bit. I had already touched on it, so let's just backtrack a little bit. So when you look at these and you can see that there is a good convenient number that both of these can be raised from. So for example, 2 to the fourth power is 16, 2 to the third power is 8. So if you have a nice convenient common base, you can rewrite uh, your numbers in terms of that common base. So 16 is 2 to the fourth, and 8 is 2 to the third. Common base, same base, and that's going to be very convenient for when you solve them. What you need to do is you need to multiply these powers. And since you've multiplied the powers now, because power to a power rule, since you have the same base, the exponents, in order to get the same number, would have to be the same. So the 12x equals the 3. Like I said, we've done this already, but we do need to backtrack over it and remind you of it in this section. So since 12x equals 3, x equals 1/4, because 3 divided by 12 is 1/4. Okay, so you have that as a method if you see very clearly that you have a common base that's coming out. So you're thinking of your powers of 2, your powers of 3, your powers of 4 and 5, and those that are easy to figure out. All right. Because when it gets to be where it's not something that jumps out at you easily, we have other methods that you can use rather than making yourself always trying to force this, because it doesn't always work. We can look here. Here's one. If you think about what the common base is, this probably jumps out a little bit at you that these are powers of 3, 3 times 3 times 3, and then 3 times 3 times 3 times 3 times 3. So we have 3 cubed, 3 to the fourth. Power to a power multiplies exponents. Both 3's to the same power in order to get the same number. So 9x equals 4, and x equals 4/9. So nice slick little way of solving problems that are convenient enough to have common bases. Now if they have different bases, and we've actually done some like this also, but we're going to look at another method because all of these logarithmic strategies work. So here some of you might be thinking, oh, okay, log base 15. Okay, you could do that. That will work also. But another thing that you can do is take the log of both sides. This is going to set us up for calculator use very easily because our calculator does have log base 10. So we can always deal with that. All right, so I've taken the logarithm of both sides. So how is that helpful? Well, that's helpful because then I can use a property of logarithms to take this exponent and bring it down because I'm solving for x. Okay, because the log of something to a power, this number can come out front. And then in order to solve for x, I can divide both sides because this is now just plain old multiplication. I can divide both sides by 3 and log of 15. Then it's a matter of taking this answer you got and putting it into the calculator carefully. Okay, well, let's see. What do I mean by carefully? What I mean by carefully is that your calculator will always use order of operations. So if you don't remember to encase the denominator in parentheses, it's going to give you an incorrect answer. So I can put in log of 285 divided by, and then parentheses around your denominator so it remembers to treat this as a group, 3 times the log of 15. And then notice it gives an automatic parenthesis here, but I need to close this parenthesis to make it work. And your 84s make it look a little bit more elegant than this, but we'll just do this. So 0.696 or 0.6958, depending on what place value you're asked to round it to. This is the tenths, hundredths, thousandths, 10,000ths, just so that you remember, just in case. Or we could call this 4 decimal places if we wanted to round to this power, or round to this decimal, or round to this decimal, whichever one you're asked to do. So 0.6958. Okay. Let's do another one. So practice this one, and you can scroll through quickly if you need to. And 5 to the 2x, it still counts as watching the whole thing if you do this and skip through to see if you got your answer right. So 5 to the 2x equals 130. Logarithm of both sides. And then the 2x gets dragged around to the front. Divide by 2 and log 5. Use your calculator carefully, remembering to put in the parentheses. So I'm going ahead and doing that. Log of 130, because it does you no good to get the good steps done and then not do the last step correctly. 2 log 5. So you say, okay, well, how do I know that I didn't make a mistake? Because you have 1.1512. Okay, well, in order to check to make sure you didn't make a mistake, you want to plug this back in here. Now this is an interesting thing. I want to take 5 to the 2x power. 5. And since this is a decimal rounded, it wouldn't come out exactly right. But if I want 5 to the 2 times, now there's a way to pull up the last answer you got, which is the second of this minus. So here's 5 to the 2 times what I got power. And if we did it right, we should get 130, which we do. So that's your way of checking. And that's a good strategy for you to have. Okay. Another thing that you can do is solve by graphing. Now on the graphing calculator, we've done this type of thing before. So a lot of things we're doing today are putting together stuff that you've done in the past. So I've gone ahead and taken the liberty of putting these equations into your calculator. Because if y equals this, and then another y equals this, and you find the intersection of these two numbers, it's going to actually give you the answer. Now, when I try zoom 6, it's not showing me enough of the graph. It's not showing where those two things intersect. So what we need to do is we need to make sure that our window is set, if you remember adjusting the window, so that it goes past the 6,000. Because if it doesn't go past the 6,000, and y2 equals 6,000, think about that. y2 is a horizontal line up at 6,000, and we only are going to 10 with the zoom 6. So what we need to do is we need to change our window. I want it to go well beyond 6,000 on the y-axis because I want to be able to see the whole thing. So I'm going to go ahead and pick 7,000. Now remember, to keep it like that, I have to hit the graph button, not the zoom button. And then it shows me my new graph. Here it comes. There we go. And then I can calculate the intersection. So I need to go second, trace, which is the calc. I want to go down to intersection. And this is the one that goes first curve, enter. It goes to the second curve. I want to hit enter. And then they want you to guess where the intersection is. So we move it close to where the intersection is. And hit enter. and then it gives you your answer, 2.0918. 2.0918 from your calculator using that intersection method on that. So that's kind of a nice slick way of figuring that out. Okay, we can solve these by graphing. Let's put those in the calculator and give that a shot real quick. I need to. Now in this case, I'm going to want to make my window go past 800, and this one I want to make it go past 400. So let's just do those. Y equals, and we'll clear these out, 7 to the 4x power. And 800. And then we zoom 6 it. And do make sure, some of you, if you have an error, might mean that you've got something in your stats. So make sure your plots are off. There's always that to think about. I want to change my window. Let's go up to 900. So we're past the 800. And graph it. And we're going to calculate the intersection. It's down at 5. You can always hit the number 5 too. It's a little faster. You just can't see me do that. Here's our blinking thing for our first curve, enter. Here's our second curve, enter. Move slightly closer to where the intersection is, hit enter. And we get 0.859 or 0.8588. And then you could do the same thing with the other one. I'll just run through this real quick so you can see. It's always the same process. Y equals 5.2 to the 3x power. Don't forget these parentheses here either. If you're getting the wrong answer, check your parentheses. And this is 400. Zoom. I'm going to change our window shortly. Even if we don't see the whole thing, we know what's going to happen with these. Let's go to 500 and graph it. And calculate the intersection. First curve, second curve. I'm guessing it's about there. And boom, 1.2114. All right, so there's that part. And continuing to move on with this, okay, when we're trying to solve a logarithm and it's in logarithmic form, what you can do is you can consider the base and rewrite it into exponential form. Remember, when there is no base, it's a 10. These are actually super easy. 10 to the negative first power equals 2x. Log base 10. 10 to the negative first power equals 2x. And then divide both sides by 2. If 10 to the negative first is 0.1. Divide by 2. And you get 0.05. That one's already done, but let's just check it to make sure that you're right. We take log of 2 times 0.05, which is log of 0.1. And you can check that either by hand in your head, because 10 to what power gives you 0.1, or because it's a regular logarithm, you can just take log of 0.1 to double check to make sure that you were right. And you get -1. So nice, easy thing. Today, hopefully you're not finding it too difficult, but you do need the practice. And as you had seen, I had taken quite a lot of the practice things out so that you can do this and just make sure that you're mastering the concepts. Okay, things get harder and harder as we go on, as you know. I'm trying to solve for x, so I can first of all divide both sides by 2. Because to get rid of this one, I wouldn't want to bring this up as an exponent. That's just not going to be helpful because I can break this down more easily just by getting the logarithm by itself. Then we can take 10 to the second power equals 3x plus 1. 10 squared is 100. Doing your calculation, subtracting 1, dividing by 3, we have that answer. And then checking your work by plugging it back into the original equation. You always want to go back to the original to see. So 3 times 33 is 99, plus 1 is 100. 10 to what power gives you 100? 10 to the second power gives you 100. There's your 2. And that does give you a 4, which was like the original problem. So that one's done. Once again, properties can help you. Don't forget your properties. This minus, when you combine it into a single logarithm, don't forget that goes into the division category. So we get log of 6 over 3x when you consolidate here. Then you can simplify because the 6 and the 3 can divide out. Now base 10, 10 to the negative second equals 2 over x. 10 to the negative second, 0.01. Which if you don't remember, you can either use a calculator or you can do 1 over 100. That's also the same thing. 1 over 100 is going to give you opportunity to cross multiply and solve just as easily. This x in the denominator, make sure you bring it up by multiplying by both sides. The thing that sometimes people will make a mistake on is trying to divide both sides by 2 here, but that doesn't work. The 2 is already in the numerator, the x is not, so be careful with that. Then divide by 0.01 and get yourself 200. We check it by plugging it back in. So log of 6 minus log of 600. And if you go ahead and throw that in the calculator just to convince yourself, log of 6 minus log of 600. And that gives you -2, which is what we were originally looking for. So we've got that, and that's a good thing. Let's move along. Almost there already, actually. This one's fun, okay? This one ends up getting us back into our quadratics, where we do really need to back into a little bit. You have this plus, which implies that when you put it together, you can use multiplication. So we're going to do that. Okay, log of x minus 3 times x. It's this whole thing, the logarithm of this whole thing. So what we can do is change this into x squared minus 3x. Okay. Now it's log base 10, so 10 to the first power equals x squared minus 3x. Now we're in quadratic territory. Factoring doesn't help here, but when we move the 10 over by subtracting it from both sides, we have something that's very easily factorable. You're looking for factors of -10 that when you add them together you get -3. So -5 and 2 works for that. And then you can break that up so that you get x equals 5 or x equals 2. Now just like always, we need to check for extraneous solutions. So we go back in and we try to work this out. And we need to figure out to see if this works. First of all, the first one does. 5 minus 3 plus log base 5. That works. But let's see what happens when we try to take logarithm of -2 over here on the other one. Okay, we get an error. It's a non-real answer. So we're not going to be able to take a logarithm of a negative. So when that bogs down there and you can't make it work, because 10 to any power is not going to give you -2, 10 to any power is not going to give you -5, then we say that's a no. So this one comes out to be extraneous. X equals 5, when you plug that in, actually works. So you do need to be in the habit of checking your work. Okay? And just hold on a second. Okay, so on page 471 of your text is a model problem that shows the idea of exponential decay in the terms of forestry, where they are harvesting a certain amount of trees in a forest and it's declining at 7% per year. So it gives you an example of using the decay model. Now, unfortunately, because of the amount of time in our year, I basically pulled out the word problems for you, but just understand that it's kind of like the exponential growth idea but I already talked about that with the exponential growth, like you put money in a bank account. But in this case, it's a decay, so it's going down instead of up. But it's a tree company that's harvesting trees. So it's the same basic idea with that function that you used. It's not the PERT one, it's the one where you had the same thing happening yearly with the exponential growth, or in this case exponential decay. And so if you want to take a look at page 471, that's fantastic. It's just a matter of we need to make sure we get through some other things, so I have chosen to omit that. All right, so that's it for today, and what I would like you to do is get your assignment done, so I'm not going to hold you any longer. Have a really wonderful day. God bless you.